The visualization experiment, the beaker to beaker. Okay, now when I was sitting in acoustics class one day, I heard about this experiment. I was like, man, that fits creation so perfectly. So, let me draw this for you. You see a circle of concern and a circle of influence. This is, imagine yourself looking down on a table at two beakers. You have a small beaker and you have a very large beaker. Both these beakers are filled with some kind of fluid, water, liquid, plasma, elemental particles, everything we've been describing all along. Okay. If this beaker is filled with oil, and this beaker is filled with plain water, what you're going to do is if you see a light wave or a sound wave or anything go in this, we use light sound. If you see light go in this beaker, what you're going to happen is, because this is much denser than this medium, what's going to happen is some of it is going to go into that medium, but most of it is going to be reflected off that medium. And you're going to see this beaker in it. Okay? Now, the opposite way is if I fill this medium up with oil and this medium up with water or less dense oil or whatever, this was more dense than this medium, and I sent a light wave through that, well, because of scattering and absorption that's going on in this medium being more than the scattering and reflection of this medium, which is water, you're going to get 100% transmission into the water. And so there's not going to be any reflection get back to your eyes, and you're not going to see the beaker of water in the middle. So you got all the absorption is going to be absorbed by this medium. And even though light will go into this medium, you're not going to know it's there because this outer medium is absorbing all the reflection, refraction, diffraction of light, and all the energy is going into it. So go back to what we were talking about before. Okay, so this is the sun. All right, we're on planet Earth. We got a couple satellites. They're looking outward from our bubble. All right, our bubble contains a specific density of medium, and outside of this, we have another type of density of medium. This is cosmic microwave background up here. This is the plasmasphere from our sun, the extent of it. All right, this is the Milky Way galaxy we're traveling through. Okay, what if we were looking into another firmament layer, and this was oil, this was something else, but yet the stars were set different locations in these firmaments. The scripture says to give light upon the earth. All right, so we'll be able to see all these stars. But what's going to happen to the speed of light as it's traveling through these different layers? We may see on Earth the speed of light traveling in interferometers at a specific speed. But what we're trying to show here is that in this medium, it can be completely different because it's a different type of medium. It could be water here, oil here, it could be hydrochloric acid here. Okay, so all these things are going to change the speed of light through different mediums and how we observe that light as it's passing around these stars or coming close to these stars. Just we saw those images up front as the light, as the water was traveling around those objects. It's going to bend, diffract, reflect, absorb, and transmit. Some of it's going to transmit, some of it's going to be absorbed by these different mediums. It's called gravity bending. Okay, I'm going to get to that more in a second. So, all of this sounds like pure speculation, right? So do we have anything in current observational data that supports this idea? Yes, we do. Now this is our atmosphere. And as you can see, it's collected in layers. And as you notice, you see what's called a tropopause above the troposphere. The tropopause is approximately 4 kilometers thick. Okay? That tropopause creates a double layer between the stratosphere and the troposphere. Now, and this isn't just for, there's not just a tropopause, but there's also a stratopause, a mesopause, an ionosphause, and then you go out into the magnetic layers of the Earth beyond that. Okay, so now we see right here atmosphere as we're looking outward into space. There are different levels and different densities of different gases in each of those layers. All right, so in our own Earth atmosphere, we see this phenomenon. As you go outward from our own atmosphere, you got a magnetopause and a magnetosheath. You go on out farther, that little dot is the sun, and that termination shock is the farthest out that we've ever gone, number one. Number two, it's as far out as the sun's influence is, or the plasma the sun ejects. So you have a helopause and you have a helosheath. Right? So the helopause is outside the helosheath beyond termination shock. Alright, so we see all of these firmament now as we look outward into space. Each of these firmament contain different types of mediums, different concentrations of mediums, different temperature of mediums. Alright, so now, what is a double layer? Go back to double layer. So what is a double layer, and what are some of its properties as explained by plasma physics? A double layer is a structure in a plasma that consists of two parallel layers, just like you see there, the tropopause. Two parallel layers. Particles which enter the double layer are accelerated, decelerated, and reflected by the electrical field. Now we know from past scientific experiments that our atmosphere is full of electricity. Alright? It's just basically an electric field. The plasma sphere of the sun is an ionized gas field. The plasma sphere of the universe, of the galaxy, the Milky Way galaxy, is contained in another bubble, and it's called a plasmasphere, or the sphere of influence of the galaxy. Beyond that, then you have the superclusters, just like the Virgo cluster, and that's what you saw in the map of the galaxy earlier with all the white spots on the black background. Everybody remember that one? So each of those clusters then also have plasma spheres, plasma pauses, all those kind of things, just like we saw a second ago with the sun. Now, the widths of these layers can vary from a few millimeters in a laboratory to thousands of kilometers in space. As we see here with the tropopause in our own atmosphere, it's 4 kilometers. Okay. Which, because of acceleration, deceleration, and attenuation we mentioned earlier, could make where we see the stars to be and where the stars actually are quite different than what we've established based on 186,000 miles per second in Einstein's relativity theory. Now this is extremely important because God set, according to Genesis, the stars into the firmament. Now if a foreign object is inserted into a plasma, now remember, each of these firmaments contain different qualities of plasma fields. If a foreign object is inserted into a plasma, a double layer will form around it, separating it from the background sea of light and plasma that it's inserted in. And what did we talk about earlier? There is a background sea of light that is the original creation. And then when God started to create things, He called the planets forth, and He spoke the stars forth. It automatically created these atmospheres around them as they were inserted into the background sea of light, the plasma, that we saw at Rick Scientist, the fundamental waters of the universe. This is true from particles like electrons and protons to stars. And this is why Dr. Hage, the astrophysicist, said that we see things against this background sea of light because they are over and above the background sea of light, this very fundamental element of the universe. This is why we see stars. Why? Because they're reflecting this background sea of light. Okay, now, they're above and beyond this background sea of light, sorry. This is true for all stars. It is this effect that I'm trying to describe here that confirms the prediction made by my theory as to why we see any particles that matter at all. Because they are an insertion into this plasma.